Hello students, hope that you are all well. In my last video, we have done the first application of the Gauss's law where we have found the electric field intensity at a point due to a line charge. Today in this video, we are doing the second application of the Gauss's law. But before that, I want to discuss something about the Gauss's law, and that is how and where we have to apply the Gauss's law. So here the Gauss's theorem is like that: E dot ds is equals to q by epsilon naught, where there are certain quantities like E is electric field, ds is the cross section area of the Gaussian surface, q is the total charge, and epsilon naught is a free space permittivity. We can write it here in this form also. Just dot product of E dot ds is equals to E ds cos theta is equals to q by epsilon naught, where this theta is the angle between the electric field vector E and the ds vector, that is the surface vector. In any equation of mathematics, we know we can always find out one quantity if the other quantities are given to us. So this is like that. This is like an equation, and where we have to find the value of E. So we have to know the value of ds, q and epsilon naught. That is, we have to know the cross section area, that is ds. We already know the value of epsilon naught, it is a constant quantity, and we have to know about the different type of charge distribution. So what is a different type of charge distribution? We already know either it may be a point charge, either it may be a line charge, that is a line containing a constant charge, either it may be is a spherical shell, or it is a solid sphere, etc. and so on. Now we have already done our first application in the form of a line charge. So we already know how to apply the Gauss's theorem. But to make it more lucid, we can write it step by step format, what to do exactly. So the step one is take the point where we have to find the electric field. Step 2, construct a Gaussian surface through the point. Step 3, total charge enclosed by the surface. So we have to find the total charge enclosed by the surface. That is, we can represent as Q. Next step 4, the total cross section area of the Gaussian surface. So we have to find the total cross section area of the Gaussian surface, which is the closed integral of ds. And then we have to apply the Gauss's theorem. Like that, E dot ds, where we can find the value of ds, we have found the value of q, and we know the value epsilon naught. So we can now find the value of E if we know the value of ds, q and epsilon naught. Now let's do the second application of the Gauss's law. Here it is. We have to find the electric field intensity at a point due to a uniformly charged thin spherical shell. So spherical shell is like a hollow sphere, just like a football, empty inside. So now let us consider the shell is containing the total charge capital Q, and the radius of the shell is capital R. From the consideration symmetry, the electric line of force are directed towards outward radially. That is, the electric line of force are directed outward in radial direction. Now we have to find the electric field intensity due to this shell. We will do it for 3 different cases. If the point is outside the shell, if the point is on the shell, and if the point is inside the shell. So let's start the first case, that is at a point outside the shell. Let us take a point P outside the shell at a distance small r from the center of the shell. Here small r is greater than capital R, it's obvious that. Let us consider a sphere of radius smaller which is act as a Gaussian surface. Here, the total flux enclosed by the Gaussian surface, we can write it as closed integral of E dot ds, or we can write it as E closed integral of ds, because E is a constant quantity and this ds is the total surface area or the total cross section area of the Gaussian surface. As the Gaussian surface is in the form of a spherical shell, so by the formula of sphere we can write the value of cross section area as 4 pi r square, because this is a spherical shell of radius smaller. And the charge enclosed by the Gaussian surface, we have already know that this is the total charge Q. So the charge enclosed by the Gaussian surface is Q. Now if we apply the Gauss's theorem, E dot ds is equals to Q by epsilon naught, and just put the value of ds here, E into 4 pi r square is equals to Q, the total charge, divided by epsilon naught. From this equation we can find the value of E as Q divided by 4 pi epsilon naught r square. So this is the expression of electric field intensity at a point outside a spherical shell. If we write it in the vector format, it has the expression of Q divided by 4 pi epsilon naught r square into r cap, where r cap is a unit vector directed radially outward. So this is the r cap, the unit vector directed radially outward. So this is the final expression for the electric field intensity at any point outside a spherical shell. So we can find it from this expression, that is the electric field intensity at any point outside the shell is inversely proportional to the square of the distance from the shell. And field intensity outside the spherical shell is same as if the whole charge were concentrated at the center of the spherical shell. So this is our first case. Here this is the second case. Here we have to find the electric field intensity at a point on the surface of the shell. Here the point is situated on the surface of the shell. So obviously small r is equals to capital R for this case. Now we can find it, the total charge enclosed by the surface, that is the Gaussian surface or the shell, is actually capital Q. So if we apply the Gauss's theorem, that is E dot ds is equals to Q by epsilon naught, here E closed integral of ds, where closed integral of ds is the total cross section area of the shell, is equals to Q divided by epsilon naught. So if we put the value of the total cross section area of the shell as 4 pi capital R square is equals to Q by epsilon naught. So we can find the value of E as Q divided by 4 pi epsilon naught capital R square. And if we write in the vector format, it becomes Q divided by 4 pi epsilon naught capital R square R cap, where R cap is a unit vector directed outward radially. So this is the expression for the electric field intensity at a point on the surface of the sphere. Now again we know the surface area of the sphere is 4 pi capital R square. And we know the total charge enclosed by this surface is capital Q. So we can find the total charge divided by the total cross-section area, that is the charge per unit cross-section area, that is sigma is equals to Q divided by 4 pi capital R square. This sigma is known as the surface charge density. So now if we put the value of sigma in the expression of electric field intensity E, then we can have the expression E is equals to sigma divided by epsilon naught. So this is another example or another expression for electric field intensity at a point on the surface of the shell. Now this is the third or the last case. Here we have to find the electric field intensity at any point inside a spherical shell, which is a uniformly charged spherical shell. So for that, let us consider a point P inside a spherical shell at a distance smaller from the center of the shell. For this case, our smaller is less than capital R, where capital R is the radius of the spherical shell. Now, it is a common fact that the charge are always resides only on the outer surface of the shell. So here the Gaussian surface does not enclose any charge. Therefore, the value of Q is equals to 0 for this case. Now if we apply the Gauss's law, that is closed integral of E dot ds is equals to Q by epsilon naught, we can write as E into ds means the total cross-section area of the Gaussian surface, that is 4 pi smaller square is equals to, we know the value of Q is 0, so this is 0, and for that we can find the value of E is equals to 0. So there is no electric field intensity at the inside of a charged spherical shell. So as the total charge is distributed on the surface, on the outer surface of the shell, so no electric field will be there inside the spherical shell. So in our video today, we have found the electric field intensity for a thin spherical shell. When the point is outside the shell, the expression is this, E is equals to Q by 4 pi epsilon naught smaller square into R cap, where smaller is the distance from the point from the center of the shell. And if the point is on the shell, then electric field intensity is equals to Q divided by 4 pi epsilon naught capital R square R cap, where capital R is the radius of the thin spherical shell. And inside the shell, as there is no charge enclosed by the Gaussian surface inside the spherical shell, so therefore there is no electric field inside the spherical shell. So this is our second application of the Gauss's law. In our next video, we are trying to solve other few applications of the Gauss's law.